So last time we implemented multiple frames in flight, and we still have to handle the swap chain recreation. But let's delay this again and instead try to actually draw something and see if our setup even works at all. So how do we draw with Vulkan? Well, we have already set up our render path using this begin and end rendering commands, which is of course part of the dynamic rendering feature. That sets up a frame buffer, so the attached images to draw onto, right? Now, inside this render path, between begin and end calls, we add the actual draw commands. And there's a whole bunch of different ones, allowing for different drawing techniques. So there is this CMD draw, then there is CMD draw index, CMD draw indirect, and much more. And pretty much all of them start with the CMD draw prefix. Now, if we take a look at the simplest CMD draw command, you see that we passed a number of vertices to process, and it also supports instance rendering, so you also pass the number of instances to draw, as well as the offsets to the vertex and instance IDs. But of course, as you can imagine, this is not enough to get stuff drawn on screen. This command just instructs the GPU to execute the graphics pipeline, but the pipeline must be set up and bound to the draw call. So let's see. Let's imagine that we want to draw a simple single-colored triangle, right? The hello world of graphics programming. So we can use the CMD draw, of course. So let's fill the arguments here. We pass the command buffer. The number of vertices is 3, of course. 1 instance, and 0 for the offsets. Next, we need to set up a pipeline. And before that, we need to implement shaders, right? The most basic pipeline setup consists of a vertex shader followed by the fragment shader. So the vertex shader processes vertices, then the pipeline goes through rasterization, and for every fragment, so more or less for every pixel, the fragment shader will be executed to calculate the color of the pixel. Nowadays, there are more options actually, because for example, there are such things as mesh shaders, for example, that can completely replace everything that comes before rasterization, so even vertex shaders and stuff. And there are tessellation shaders and things like this. And also things like mesh shaders are only supported starting from, I think, GeForce 2000 series and later, so maybe not a good idea to use them just yet, if you want to be compatible. And also for the shading language, you have multiple options. You can use the classic GLSL one, right? That exists since OpenGL, of course, but it was extended to support Vulkan features, and it's a kind of a go-to language with Vulkan. But actually, if you install the Vulkan SDK, which is something that maybe I should have mentioned in the very first video, of course, but I assume that you have Vulkan SDK installed. That actually comes with multiple shader compilers, including the GLSC for GLSL. Then there is DXC, which is like DirectX compiler or whatever, which compiles from the HLSL language, also to a Vulkan compatible SPIR-V bytecode, of course. And then there is this SlangC for the newer shader language that is kind of gaining popularity. It's called Slang. Kind of a terrible name for a shader language because you can't really easily search for it, but still, the language is quite interesting. You could use that as well. I'm gonna use GLSL, so the classic one. There's a ton of examples with GLSL, and it's pretty straightforward to use. So let's write a pair of basic shaders that will draw us a triangle. So let's create a shaders directory, and inside let's create shader vert GLSL for the vertex shader, and then shader frag GLSL for the fragment shader. So we can start with a language version definition like this, with a pound version. 450 is one of the most recent ones. Then we just create a main function, and the purpose of this main function is to set up the GL position vector. That is a vec4, so it's a homogeneous coordinates. So you supply x, y, and z, right? And then you supply w, which will be used for perspective division. You can read about this. We will not focus too much about this because this is more about how to set up Vulkan and not general graphics programming. But still, let's write a very basic triangle shader. So we will have some position variable, which would be a vec3, and we will use one as w. So let's introduce a local variable for the position vector. And then for now, let's just hardcode some positions. So for the very first vertex, So the vertex with the index 0, we will use this coordinate, right? So to the left, to the top, and 0 for the z coordinate. Then for the middle one, we're gonna use the center horizontal coordinate and 0, 5 down. And the third one will be like the first one, but on the other side, right? This should give us a down pointing triangle at the center of the screen. Yeah, the coordinate space here is something called clip space coordinate, which represents your screen with coordinates from -1 to 1 with 0 at the center of the screen, right? And maybe this is a little bit surprising, but in Vulkan, -y goes up. So the first and third vertex will be actually on top and not on the bottom. I think in OpenGL this is flipped. But anyway, this should be enough for the vertex shader. Let's go to the fragment shader now. Let's also add a version define. Then we need to specify an out variable with the location layout attribute for each of our color attachment. And since we only have one color attachment, this one, right, our swap chain image, we will simply specify a single out color at location 0. Then we also have a void main function, and the purpose of this function is of course fill these out variables. So for now, let's just use a solid red color. Something like this, right? 1 for the red, 0 for green and blue, and 1 for the alpha. So this will be a full red color. So now we need to compile these GLSL shaders into this per-v bytecode. And we can do this with this GLSL C compiler. I will just add it here to my just file. Of course, if you're using any other build system or script, you can do it differently. But for now, I'll keep things simple. Add this build shaders task, which is a dependency for building. And then I'm gonna just hardcode the commands like this without any discovery. So I will invoke GLSL-C on the vert and frag GLSL. I will specify the shader stage, so vertex or fragment, and the output file path, which is kind of the same as the source path, but with SPV instead of GLSL. So let's try to build that. So the compilation seems to have worked. We have the SPIR-V files here, and they should be ready to use. The program of course fails, and the validation layer complains that we invoked the CMD draw without actually binding any pipelines, which is something that we will be doing for the rest of this video. So traditionally in Vulkan, you would be using this cmd bind pipeline command to bind a pipeline for your draw calls. And if we check the arguments, it needs a pipeline bind point and the pipeline. So the bind point is graphics, compute, or some extension ones like ray tracing, for example, and stuff. And the pipeline is something that you create in advance using your shaders, using this huge structure, graphics pipeline create info, right? Where you specify all your shader stages, then you specify how you want to pass the vertex input, the viewport states, the rasterization states, all the stuff you have to pass. And also, you can set some of those state as a dynamic state, like this, using this pDynamic state. And here you can specify quite a lot of stuff as dynamic, meaning that you don't have to pre-build a pipeline in advance for some of these parameters, like, you know, viewport or scissors or like your cal modes and whatnot. And there's a lot of them. But instead, you can set them dynamically here as a command. For example, if we are drawing lines, we can set our line width as a dynamic parameter. And then we can use this cmd set line width to actually set the dynamic value. So this is all and good, but with this approach, we still have to build a pipeline in advance before using it. And this is something that we were also doing, for example, in the SDL GPU series or in Sokol series. And this is what has believed to be, I think, a source of performance for Vulkan, because, well, you can compile all the parameters in advance and then provide it to the driver, and hopefully the driver does the right thing with it and optimizes the hardware for that. But this actually proves to be pretty annoying to work with, because normally in a render you want to have some notion of materials, which would include different shaders and different dynamic parameters for the shaders, different settings, like how depth and stencil is handled, or what is a front face and stuff like this, right? And normally you would need to basically have some system to generate predefined pipelines for different materials and also try to cache them and reuse them, and this gets pretty complicated, especially if you compare it to the older APIs like OpenGL, where you could just set things dynamically and not think too much about this. Which is thankfully also an option in Vulkan actually. So you can see there's this blog post on the Kronos website that you can use Vulkan without pipelines today, right, from 2023. And this talks about this nice extension called VKX shader object, which basically allows you to compile your shaders and only your shaders, and then just bind the shaders directly and set all the required pipeline state dynamically using this vk cmd set whatever commands. And I didn't look too deep into performance or compatibility implications of that. I think it's pretty close to how NVIDIA hardware works actually under the hood anyway, but apparently it's a different story on AMD or Intel. But as far as I know, all those drivers are also implementing this extension nowadays. But anyway, even for the drivers that do not have this extension, you could actually have an API extension layer that emulates this extension, I believe by just collecting all the state change commands and basically building your pipelines, and it tries to do it very efficiently, right, using any available features that the driver actually provides. So this should work. And this is what I'm gonna use for this series, because yeah, maintaining pipelines is not that fun. So let's start by enabling the extension and also the compatibility layer. So first let's start with the compatibility layer, because it's literally a single line that we have to add. So here in create instance, where we add the validation layer, we simply add this extension and that's it. I mean, technically you should probably check if the extension is available or not, but we will not do this for our simple Hello World application. And what this extension will do is it will try to emulate the shader object extension if it's not provided by the driver. But if it is provided by the driver, then it will do nothing. It will just turn itself off. So that's that simple. Next, we actually need to enable the actual device extension for the shader objects. So let's go to the create device function. And right here, where we have our swap chain extension name listed, let's also add the shader object extension name like this, ext shader object extension name. This will enable the extension, but funnily enough, the extension will not enable the actual feature of shader objects, which is something that we need to explicitly enable very similarly to this Vulkan 1.3 features by using another extension for the device create info structure. So let's add it to our next chain, just like this. So after assigning the Vulkan 1.3 features to our next pointer, we also extended with this physical device shader object features ext structure with the fitting S type, of course. Then we are referencing the previous extension, so with pin next, and then we simply say shader object equals to, right? This will enable the shader object extension, and this is everything that we need to do to actually have the API available and extension working. So now, instead of creating a whole pipeline, we just need to create our shader objects, right? And we have just written a vertex and a fragment shader, a basic pair of shaders. Let's add a field for them in our global structure. Let's simply name it shaders, and that would be a pair of the vk shader ext type. Now let's go to our main function, and before our main loop, let's add create and destroy shader function calls. Right, something like this. Let's create the actual procedures like this. And now we need to call this create shaders ext procedure. That takes, of course, a device. So that takes a number of create infos for the shaders, then as usual, the allocator callbacks, and a pointer where to store the results, right? Obviously, the memory on that pointer should be enough to accommodate the number of shaders that we are creating, right? We are creating two shaders, right? Vertex and fragment. Now let's actually have a fixed array of shader create infos. Like this. We will fill them later, of course. For now, let's just add a pointer to this fixed array as an argument. In Odin, you can either just have a pointer to the first element, like you would do in C, or you can also do a raw data of a pointer to a fixed array. So that's the syntax in Odin. I myself only learned about this recently, but anyway. Next we specify the allocation callbacks. As usual we use nil. And finally we need to specify the destination pointer, and since it's a fixed array, we will do the same raw data trick. Something like this. Let's wrap this in vk check. And now let's take a look at this create info structure. So you can see there are quite a lot of fields. There are some flags to fill, there is stage to specify, right, which stage this vertex is for, vertex, tessellation, fragment, geometry, and so on. Then the next stage, we'll get back to that. Then you simply specify which kind of code it is, so that can be either binary or SPIR-V, and we are using SPIR-V, so we will specify that, of course. You can precompile binary shader for your platform if you're doing an actual game. That could be a good idea, but we'll just be using simple SPIR-V shaders. Then you specify the byte size of the code, the pointer to the code itself. Then pname is the entry point function, and the rest is about what shader expects as an input. We will get back to that. And the specialization info is for providing values to constants in the shaders programmatically, so that's also something that we are not gonna use. As you can see, first we need to load the code somehow, so let's do that quickly. We will need OS package, so let's import that, core OS, right? Then let's have some load file function, so that will take a file name, return a slice of bytes, and we can simply use this read entire file from file name procedure, pass the file name to that. Maybe we should also pass an allocator explicitly to it. Let's add it also as an argument, runtime allocator, because we'll be using temporary allocation for loading shaders. And that's gonna return the data and whether it was successful, right? The usual Odin pattern, data okay. Let's also quickly add an assert that it was indeed okay and log an error if it wasn't, and return the data, right? Nothing too fancy. Now let's load our shaders. Something like this, right? We load the SPV file for the vertex shader using the temporary allocation. We do the same for the frag, and we can already fill the code size and p code pointer as well as the p name. So let's do that. Code type is SPIR-V, of course. Code size is simply the length of the byte slice. Pointer to the code is, of course, raw data of that slice. And the p name is the string constant main, because that's how we named our entry point functions. Now let's see, the stage is, even though in Odin it's specified as a bit set, right, like this, we should only provide one value here. So for our vertex shader, we will of course use this vertex, like this, right? Now this next stage is another stage flux bit mask that should specify which stages may be used logically as the next shader in the pipeline. In case of vertex shader, this will be of course the fragment shader, so let's quickly specify that. Next, let's quickly take a look at the flags. So one interesting one is this link stage. That means basically that all the shaders that we create in the same shader create info call, of course with proper stage and next stage fields, will be linked together, which should allow for better cross-shader optimization. So maybe it's a good idea to use that flag at least. Let's set it like this. Now the subgroups are related to compute and mesh shaders, so we can ignore those for now. No task shader is also related to mesh shaders, so we are ignoring that as well. The dispatch base is related to compute shaders, we're ignoring that of course. And all the other ones are for much more advanced usage, like variable shading rate and density maps, and device generated commands for this indirect bindable and so on. So the only flag that we are gonna specify is this link stage. So with that knowledge, let's fill the fields for the second shader. Like this, right? It's pretty similar to the vertex shader, but instead of vertex, it of course specifies the fragment as its stage, and there is no next stage. Everything else is the same. Let's also quickly implement shader destroy. And we are doing it normally. For each object, we simply call the destroy function like this, right? vk destroy shader x, we pass the device, the shader, and the same allocation callbacks as we used for creation. So that should be enough actually to already start using the shader in our draw calls. So let's go to our render loop, and here just before the CMD draw, we need to bind our shaders to their graphical pipeline stages. And we do this with the cmd bin shader cxt function. So that takes a command buffer, the number of stages. Then we need to specify a pointer to an array of stages to which we want to bind the shaders. And then we need to specify a pointer to the same number of shader objects that we are gonna bind to the respective pipeline stages. I find this API a little bit awkward, to be honest. It would be nicer if we could pass an array of some shader binding infos that would specify a stage and a shader object per element, but it is what it is, so let's do that. So for shader stages, let's add a local variable like that, shader stages. So this would be a fixed pointer of stage flags. And once again, in Odin, it's a bit set, but we are supposed to use only one variable, so we simply wrap it in curly braces. The first stage is vertex, the second stage is fragment. And we pass it using the same raw data to the pointer of fixed array syntax as we use with creation. And for the B shaders, we are of course using a pointer to our initialized shader object fixed array. Like this, right? That doesn't look too pretty, so it might be a good idea to wrap it into some nice helper function later, but let's not do this for now. So now, if we run the application, you see that it will not complain about that the pipeline is not bound, because, well, it is actually bound. It will complain about the fact that it's not configured, because in absence of a pre-configured pipeline, you actually have to specify quite a lot of state commands before doing the draw call that will configure the pipeline. And it's described here in the spec in this section, setting state. So you see, we'll need to specify the viewport size, the scissor size, whether we want to rasterize or not, vertex input, how to assemble our vertices in primitives, right? And then depending on the shader stages, you need to specify more settings. Some of those settings are only needed to be specified if you enable the feature. For example, you only need to specify the stencil configuration if you actually enable it. So that means that you don't have to call all these commands, but you still need to call quite a lot of them. So let's do that. So the first one is this cmd set viewport with count. We specify the command buffer. Then the number of viewports is how many viewports your device is rendering onto. Normally you just render to 1, so we specify 1 here. Then we can have a pointer to an inline structure like this. And here we would specify x and y width and height, which would be from 0 to our swap chain width and height, right? Because our viewport would be the whole screen here. We can omit x and y and only specify width, height, and min and max depth. Like this, right? Except that for the viewport, width and height is expected to be f32, while our values is u32, so let's convert this like this, right? And then for min and max depth, normally it's between 1 and 0. That doesn't matter too much for us right now, but it will matter when we'll be adding depth testing and hence the depth and stencil attachment to our render path. But for now, let's simply specify it as from 0 to 1. So that's it for the viewport. Let's now specify the scissor. The similar command, cmd set scissor with count, our command buffer. So this should specify a number of scissor rectangles, so basically which areas to draw for each viewport. So we have just one viewport, so the scissor count is also 1. And we can also use the full width and height for our rectangle here. So let's inline the rect2d structure, take a pointer to it. So the rect2d contains an offset, which would be, well, an offset, right? And then the extent, which is the width and height. And scissors are in pixels, so that would be u32 values. So for this one, we can use our swap chain width and height directly, right? So the next command is very simple. Set rasterizer discard enable, according to this command buffer. And this basically controls whether the primitives are actually rasterized by the pipeline or not. We, of course, want to draw, so we will simply pass through here. Actually, I'm completely wrong. This says discard enable, so we actually want to pass false here, because we, of course, do not want to discard. There might be some use cases in which you would only want to process vertex information, for example, right? Maybe a write to some storage buffers and whatnot, and then not rasterize at all. So this is, I guess, where you would use false here, but of course that's something outside of the scope of the hello triangle. So let's proceed. Next, we need to specify the input structure for feeding the vertex buffer using this cmd set vertex input ext command. And this one is a little bit complicated, but in essence it's really similar to what we did in SDL or SOCL, and this is where you would specify all your vertex buffer bindings and how to interpret them using the standard fixed function vertex processing mechanisms. For now we are hard coding all the vertex data, and even then I don't really want to use that because nowadays you don't really need this. To be honest, you can simply read some data from the video memory directly in the vertex buffer. So we will specify zeros and nils here. So 0 for binding count, nil for the pointer to the descriptions, and 0 vertex attributes because, as I said, we will not be using that. We still have to call this command because it's required, but yeah, we'll just pass zeros here. So next we specify how to assemble our primitives using the set primitive topology command. And here is where we specify what are our primitives that we are assembling using our vertices, right? So this can be just points, this can be lines, this can be a strip of lines, and the same for triangles. We're gonna use a simple triangle list because this is the most straightforward one. For tessellation you would also use patches, right? But this is of course more advanced. So simple like that. Then we have this set primitive restart enable command. And I think this is related to line strips and triangle fans. And this allows you to specify some magic vertex indices that will break the strip or a fan and just restart the assembly. So since we are using a simple triangle list, that doesn't even apply to us, so we'll just pass false here. So the next batch of commands have to do with rasterization. So if we actually do the rasterization, then we have to specify all this stuff. So let's do that. So the next one, this cmd set rasterization samples ext command, sets the number of samples for the multi-sampled anti-aliasing. That is a thing that we are not touching for now, of course, but it's a pretty performance-friendly and straightforward anti-aliasing technique, but still, we can simply specify one sample per pixel here, and that should be good enough for us for now. The next one, cmd set sample mask ext, is also related to multi-sampled anti-aliasing, and it allows you to configure for each of the sample count which actual samples are active, so you can do this very precisely with a bit mask. Since we are only having one sample per pixel, we specify one value in the samples bit mask. So just like before, 1. And the psample mask here should be a pointer to an array of bit masks that actually activate samples, right? Since we have just one sample, we need an array of one element, and we have only one sample, so we set only one bit in that single element, which would be 1, right? Because that's the first bit activated. I know it's probably a little bit confusing, but we can actually afford not to care about this too much for now, right? And the sample mask is actually basically an integer, so we need a local variable to pass a pointer to that. Something like this, right? A value of 1 casted to the proper type, and then we take a pointer and pass it here. Next one is this set alpha to coverage enable command, which is again related to the multi-sampling, I believe. That is something that might be helpful for transparency and whatnot. For now we don't care about this, so we disable it by passing false. Then we have set polygon mode, which is an interesting one. Here we can specify if we want to fill the polygon, or we can basically can write it wireframe, right, with lines, or even with points. We want to fill our triangle, so we'll be using fill here. The next one is set call mode, and here you can basically specify whether you call front faces or back faces, or no faces at all, right? This is a useful optimization because most of the times we only want to draw triangles that are actually facing the camera, right? But for now, let's disable this. We still have to call this command, of course, but let's just pass 0 value here, like this. Then we have the cmd set front face, which basically determines what is a front face, depending on the order of vertices, right? You can specify counterclockwise or clockwise. So basically the order of a primitive vertices will tell the GPU where's the front and where's the back face, right? I believe the kind of a standard value for that is counterclockwise, so let's use that. It doesn't really matter that much anyway, because we are not doing any culling. The next one sets whether we want to have depth testing or not, and for now we don't, so let's pass false here. The next one is also of course related to the depth testing, or rather to the depth writing, so whether we actually want to write depth values to our depth attachment, but since we are not doing any of that, we also specify false here. The next one is also related to depth, and that is related to depth biases, which is a technique I think mostly for preventing Z fighting and whatnot. Also don't care about that, so false. Similarly to depth, there's also stencil testing, which we are not using, so put false there. The next one is set color blend enable, and here for each color attachment you draw onto, you need to specify if you want to blend colors with whatever is currently in the buffer, or you just want to replace them, right? We are gonna not do any blending for now, so here we specify whether we want to enable color blend or not for a number of attachments starting from the first attachment. We have only one, so we specify 0 as first attachment, and we have attachment count of 1, of course. And then we just need a pointer to some B32 false variable, right? So we do this similar to the sample mask. We introduce a local variable and put a pointer to that. I don't know, something like this, right? B32 false, so we can just take a pointer to it. And in a similar fashion, we need to specify for each color attachment which color channels do we actually want to write. So we want to write for all the channels, so we will specify RGBA here, right? So the first attachment is 0, the attachment count is 1, and here we need a pointer to a single element of color component flux bit set. Something like this, right? And here we simply specify all the channels, so RGBA, right? And I think that should be already enough. Let's try to run our application. And there is no triangle, but I think the reason for that is that we are using the same clear color and the triangle color. So let's maybe just change the color in our fragment shader to half blue or something like this, right? And finally we see our expected triangle. It only took 10 chapters. So yeah, that's Vulkan for you. Let's just quickly check that there are no validation errors. Looks like it's all clear. So yeah, if we take a look at this again, here we are configuring our pipeline fully dynamically before each draw call, right? And this is something that you don't normally do in Vulkan, but with shader objects, this is something that you can do. And this is pretty neat actually, because it's very easy to have some kind of material system that simply calls this chain of commands passing the actual dynamic values. So that kind of makes it very trivial to have flexible materials, right? Maybe it makes sense to move everything between begin rendering and end rendering into some render function, so it's kind of separated from the render setup. So maybe let's quickly do that, right? Just cut all of this, replace it with some render procedure that takes the command buffer, and just paste it in a render procedure like that, right? That should work as well. So yeah, now we have this triangle rendered in a somewhat interesting and modern Vulkan way, but there is of course still quite a lot to explore here, because we do hardcode everything, right? And we want to maybe upload some mesh data and whatnot, so this is something that we'll do in the future, but for now, stay tuned.